Dear audience, I would like to welcome everybody. I'm sure that you already know a lot about the heart, and today I will be talking about a specific aspect of it. Basically, how does the heart know when to beat, when to contract? This is related to the sinus node, of course, and this is called the heart's automaticity, spontaneous activity, or pacemaking. I will also be talking about a relatively new current or ionic current in the heart called the calcium-activated potassium current that could play a role in this pacemaking. So, as you know, the cardiomyocytes or the cardiac cells membrane is made up of mainly phospholipids. And ions need a way to get through this membrane, and these are the ion channels, so sodium, calcium, and potassium channels, for example. And this is regulated, so ions can't just pass through the channels all the time. This is called the channel's conductance. And of course, ions also have charges. So due to this uneven distribution of ions and charges and the conductance of a channel, specific cells can create the action potential. So you can see that in the heart there are lots of action potentials. So the morphologies are different, and today I will be talking about the sinus node's action potential. So the sinus node is located in the right atrium, and of course it is the primary source of electrical stimuli or action potentials in the heart. So by this, the heart muscle can contract and blood can flow through to the body. So the mechanism is quite complex, and there are a lot of questions still to be answered. So here you can see the action potential of the sinus node with the red line. Below that, the cell membrane can be seen, and at the bottom of the slide, the calcium ion releases from a specific compartment of the cell called the sarcoplasmic reticulum. So in the zero phase, it's the depolarization due to calcium channels here in the sinus node. So the membrane becomes more positive. This is then followed by the repolarization due to potassium channels, and then the diastolic depolarization due to funny channels, and this enables the next action potential to form. And there are also so-called beta-1 receptors in the cell membrane. These get activated when somebody is, for example, under stress or is exercising, but other illnesses or conditions can also activate this receptor. So when this receptor is activated, the intracellular calcium also rises. For this, we used isoproterenol as a substance to activate the beta receptors. So we got an increased calcium, intracellular calcium level. And because the current that we are investigating is the calcium-activated potassium current, because of an enlarged calcium level, the current that we measured might also rise, but I will get to this later. So the calcium-activated potassium channel is poorly understood in the sinus node, and we used a selective inhibitor or blocker of this current called apamine, which was first isolated from bee venom. And here's the structure of this channel. So in our research, we focused on this channel, the calcium-activated potassium channel current. So how does this work under normal condition and under a beta adrenergic activation, so when there's an increased calcium level in the cell? So for our experiments, we used New Zealand rabbits, and after we extracted the heart, one group of the hearts was enzymatically dissociated, so basically digested. And at the end of this process, we were left with isolated, so individual sinus node cells. And on these cells, we measured ionic currents and action potentials by the patch clamp technique. On the other group of hearts, we put them on a Langendorf column. This is called the Langendorf perfusion. So here's the heart, and the solution flows into the heart. So this solution mimics the blood, so the heart can beat away happily on its own. And while it's beating, we are able to measure ECG signals from the heart. So these were the two main methods that we used. So here are the isolated cells at the end of the isolation process. This isn't a sinus node cell, but The microelectrode that we use in the patch clamp technique can be seen here. So it's a very thin microelectrode that we put onto the cell, and in our experiments we poke a hole into the cell, and by this we are able to measure the ion currents flowing in and out of the cell. Of course, Professor Zachman and Erwin Neher got a Nobel Prize for this. And here's the Langendorf technique. Let's hope that the video works, sort of. It's not that smooth, but you can see that the heart is beating. Here are the electrodes, the solutions flowing into the heart. And the ECG RR intervals, of course, correlate with the sinus frequency. So these were the two methods. In the action potential measurements, we measure the cycle length from which we can calculate the frequency in which a cell is contracting, the action potential duration, so how wide the action potential is, and the cycle length variability, which is basically the rhythmicity. If the variability is small, then the contractions are smooth. If the variability is large, then it's not that rhythmic. And the ECG measurements, we measure the RR intervals, which is similar to the cycle length. So from this we can calculate the frequency, for example, if you want to, and the short-term variability, which is of course the rhythmicity again. So in our first set of experiments, you can see that we measured ionic currents. Channels opened by voltage impulses, so we use voltage impulses to open these channels. The blue line represents the control measurement, and the red one, it was after we added 100 nanomoles opamine, so this inhibitor of the channel. So the gross ionic current that we measured decreased, and this difference in the current is actually the calcium activated potassium current. So this current exists in the sinus node cells. We also looked at this channel in a functional way, so these are action potential measurements from spontaneously contracting isolated sinus node cells. And as you can see under normal conditions, when we added opamine, this inhibitor of the current, there were no significant changes in the cycle length, the variability, or the action potential duration. So everything basically stayed the same. But when we had an increased intracellular calcium level with isoproterenol, after we administered apamine, there was a significant increase in the cycle length, so the time it takes between each action potential, and the width of the action potential also increased significantly. And in our ECG recordings, under normal conditions, like in the action potential recordings, there were no significant changes, as you can see. But when there was an increased intracellular calcium level, the RR intervals became larger significantly, and the variability didn't. So to conclude my presentation, we can say that the calcium activated potassium channel only works under a beta adrenergic activation when there's a larger intracellular calcium level. By this, it helps to adapt the heart to a higher frequency. And by blocking this channel, it could be a promising therapeutic method in the future to modulate the sinus nodes pacemaking. Thank you very much.